Okay. Welcome everyone to today's installment of Paleo Perks. We're super happy to have you here. Today we will be hearing from Alessio Veneziano, who's based at the National History Museum in Paris, France. And he'll be talking about Of Bones and Bytes, the geometry and coding hacks paleontologists do want you to know. So a bit about the format of today's seminar. We will start out right now with some welcome and announcements. Then the talk itself should last about 30 minutes. After that, we will have a moderated question and answer session. And during the question and answer session, please send your questions via the chat function to the questions at PaleoPerks host, who is Nina today. A little bit of PaleoPerks housekeeping. PaleoPerks values the participation of all folks interested in the paleosciences. Please remember to abide by our code of conduct during today's seminar. Please mute yourself for the duration of your talk. You should be muted by default, but if by some coincidence you find out that you're unmuted or you become unmuted, please mute yourself just out of respect for the other listeners and for the host. You can ask questions again by chatting to the questions at PaleoPerks host, or alternatively by using the raise hand function. If you have any technical issues, those can also be directed to the questions at PaleoPerks host via the chat function. We have closed captions built into Zoom. You can use the CC button to show or hide them. Additionally, you can nominate an outstanding early career researcher here at this link, which will be shared shortly in the chat. We're always looking for new speakers, so please, we encourage you to do that. Additionally, we like to collect weekly feedback using this weekly feedback form, which helps us collect some demographic data. It's completely anonymous and optional, but it is encouraged, and it really helps us shape these seminars to be most beneficial to the paleo community. You can also find that in the chat window. So a bit more about today's speaker, Alessio Veneziano. He did his bachelor's in biotechnology at the University of Rome in Italy, and then went on to do a master's degree in ecobiology, also at the University of Rome in Italy. After that, he went on to do his PhD in physical and biological anthropology at John Moores University in Liverpool in the United Kingdom. And currently, he is a postdoc at the National Museum of Natural History in Paris, France. So with that, I'll pass it off to you, Alessio. We're super excited, and good luck. Take it away.
Yes, thank you. 1 second, I'm gonna share my screen. Hope everybody can see it. Now okay. So everybody should be able to see the most of it. Okay, thanks very much for having me here. Thanks for inviting me. I am thrilled, as usual, when I get to speak about one of my favorite topics here, exemplified in the title, the geometry and coding hacks paleontologists do want you to know. Today, so we're going to talk about geometry, we are going to talk about programming, and pretty much how I combine them into the approach that I use for my research. In line with the deceitful ad joke that I used for the title, I did deceive you. We are going to talk about all this stuff, but I am myself an anthropologist. So I do work with paleontologists. I occasionally work in paleontology, but we're gonna take a look at this subject from an anthropological point of view. I am indeed an anthropologist, as advertised. And what I do for research is using bone morphology to understand patterns in human evolution and in primate evolution. I especially use a comparative approach to understand the evolution of humans and our ancestors. And as probably many of you experience, I find myself always troubling, especially when I have to fill in a new CV for a new job application on how to describe myself. What's my title? These days, I go mostly for biological and virtual anthropologist, especially because this is not only in line with what we're going to talk in the seminar, but it's what I find most enticing about my job. to transform morphology into numbers, into 3D data, that it's what challenges me the most in a way, what I find at the same time most difficult and most challenging, and therefore funniest in a way. It's not random that I'm talking about virtual morphology, virtual applications from an anthropological point of view. Anthropologists have always been quite crafty at measuring bones. From estimating actually the brain volume by filling crania with all types of seeds. There is a vast literature about it. I really suggest you to go and check it. From that to creating devices for measuring bones that look more like instruments of torture, but they've always been very crafty. And among these ones, the one that I prefer the most, that can introduce us a bit into the world of digitalization, is the one you see on the back with the red background, that not only it has a nearly impossible name to remember or spell, but this pantagoniostato that was invented in Rome by anthropologist Sergio Sergi, it's kind of a precursor of virtual anthropology or virtual analysis of morphology in the bones. In fact, this device was invented to record on paper the two-dimensional geometric outline of crania. So you can see this was kind of a precursor of what we do today with geometric morphometrics and with the virtual applications that I myself use and develop. Fortunately, other more modern technologies came about, so we don't have to remember the name of this pantagoniostato, way too hard to do that. And with new technology, we now are able, as we all know, to transport real specimens onto our laptop. That has two main advantages. It adds two main values to our research. First, as any person that has done extensive data collection measuring on actual bones can tell you, there's always the risk of any damage lurking behind the corner. And the other aspect instead is not just about preservation. Okay, we do preserve specimens better when we are able to scan them, but we are also capable of analyzing them better. Digitization from surface scanning through laser scanning or photogrammetry up to medical CT and micro CT scanning offers incredible new avenues. Okay, the fact that we can transport the specimen onto a computer makes it possible to apply methods that wouldn't be otherwise thinkable. Maybe just Sergio Sergi could think about them by making another device that allows them to study this stuff without a computer. Okay, and that's exactly what I want you to show you today. Precisely my recipe to address this type of research, my recipe to address 3D morphology. And the main ingredients here are very simple: coding and geometry. And everything is cooked in the often unfamiliar environment of our kitchen, but you can use literally any other programming environment to do the same things. I'm just very passionate about art. So before delving into the examples that I want to show you, coming directly from my research, let's try to understand why coding and geometry and why mixing them together, it's like a winning recipe. Why coding? The reason why coding is essential when dealing with 3D imaging with 3D virtual specimens, but in general, I think in research, can be exemplified by two statements of my favorite author, Douglas Adams, author of the Hitchhiker's Guide to the Galaxy. If you don't know him, please do yourself a favor and read his books. He was also a programming enthusiast, and he left us with these two beautiful quotes. One deals with automation through coding. I'm rarely happier than when spending an entire day programming something that it would take me a good 10 seconds to do by hand. And this is exactly how we all felt. Everybody that started programming in research felt like this at the beginning. But the point is that yes, that little task, the little annoying task that you do every day, multiple times, even if it takes just a few seconds, if you make it automatic, it will last forever in a script and you will be able to use it and link it to other menial tasks that you don't want to do, but even if they're short to do, they're annoying. You know, it's like, in a way, coding allows you to save a lot of time, even if it's at the beginning, it's counterintuitive that you're saving time because you take half an hour to code something you need 10 seconds to do. But in the long run, it's really a game changer. Another reason why coding is essential, it's more into the understanding part of our research. And it's very hard to say it better than how Douglas Adams did. By the time you sorted out a complicated idea into little steps that even a stupid machine like a computer can deal with, you learn something about it yourself. And that's precisely what coding forces you to do. To arrive from A to B, you cannot just jump. You have to, well, however difficult or complex the task is, you have to reduce it into simple single steps. And that's a way for you to understand it better intimately. And that's why coding, I think it's absolutely necessary in today's research, in particular, if you are dealing with 3D. But why geometry? Well, simply put, geometry is the mathematical language in which, with which we can describe differences in morphology across individuals, population, species. And this was pretty clear already to Darcy Thompson. I don't know if you know him. He's a biologist who devised at the beginning of the 20th century a way, and he did it on paper. He devised a way to analyze differences in shape by using this grid transformation that would end up being a stronghold in what is the most useful and used method nowadays to study morphologies, these geometric morphometrics. And it's unbelievable that this person did it at the beginning of the 20th century using only pen and paper, pretty much. And the reason why this type of methods are important, the reason why it took all these efforts to do that is because we do have geometry is something we can comprehend more easily than other part of maths because it's about also visual intuition and we are visual animals. Unfortunately, to not include any bias into our analysis, we need geometry and protocols in geometry in order to be able to quantify appropriately the differences that we can already see using our own eyes. And why so geometry and coding should go together? This is pretty much consequential from the example of Darcy Thompson. Richard Dawkins described it very well in one of his books by stating that it's hard not to wonder what a man like Darcy Thompson with his mind could have achieved if he only had a computer. Okay, that's why today we have unlimited possibility thanks to the fact that we can do both. We can do geometry, that it's something that sometimes we find difficult to understand. But by using coding, by linking it to coding and computing, it in a way, at least for me, it's like this. It gets much more understandable, much more intuitive. And that's what opens up a lot of research avenues, research and analytical opportunities. If you want some examples, unfortunately, this would be rather long to explain. It's something that I use in my lessons, but to understand the power of coupling geometry and coding, I suggest you to go online and look for Alessio Veneziano, myself, on Google. You will find some examples that I put online here and there. And one is by coupling coding and geometry, you can estimate at whatever precision you want the value of pi by using a pizza, a theoretical one, of course. Another example is I provide a code and explanation to build your very own collection of 3D ammonites, 3D printable and whatever you want to do with them. So I strongly suggest you go and double check it. I would love to take the time to explain them, but they would take too long. Instead, I will go to explain two examples from my own research in biological anthropology and how coding and geometry is applied in those situations. And in particular, what I'm going to show you is examples that take into account the two main characters of 3D imaging when applied to paleontology, anthropology, archaeology, and whatever field of science, that are voxels or 3D pixels, when basically the ones we obtain through computerized tomography, and vertices and triangles that are instead the ones that more usually we obtain through surface scanning. So when we transform the object, the real object, into a 3D mesh, a 3D surface. And without further ado, let's start with the first example. The first example deals with skeletal cavities. Why are those important? Skeletal cavities make up a lot of the anatomy of a bone, okay? There is a lot of information that if we are not able to collect the bone through CT scanning and so look inside it, we'd have to break it open in order to see. One example is the brain endocast. The brain endocast is basically the brain case, the empty void that is left when the brain is no longer hosted inside the skull. Why is this important? It's important because it gives us the chance to study the brain in past humans, but also in any past species. So it has huge applications to understand cognition in human evolution and in the evolution in general. We are not always so lucky to find specimens like this, the tongue child, Australopithecus africanus, together with its endocast. Okay, so a print of the brain or of the membranes that surround the brain. When we are not this lucky, 99.99999% of the times, we have to collect it ourselves, okay? Because it holds a lot of information that we find very useful to understand the evolution of cognition in any animal that has a brain. In the past, or, it's still done actually, in order to collect the endocast, you would have to segment it manually. And that means going through hundreds to thousands of tomographic slices to select the enclosed area of the brain case, and then post-process it in order to smooth it up a little bit, in order to make it look better, But this is not only a time-consuming and very annoying thing to do. I'm kind of lazy. I'd be described as smart lazy because I tend to do anything possible to avoid working manually. So you not only you have to do this menial thing that takes forever, but you also have to consider that any manual operation on 3D images can result in mistakes. Okay, so to standardize completely the operation of segmenting an endocast, and so avoiding to do it manually, how can we do? Of course, by putting together geometry and coding. Okay, And so we did together with some colleagues now a few years ago. We took inspiration from this paper, not our paper, from some other research group. The inspiration came from the fact that this paper dealt with how to render shadows in video games, in any 3D rendering of any 3D scene. Okay, so if we are looking at the scene from one specific point, what would be the shadow that we see? If the light is in a specific place, what would be the shadow? Okay, in other words, what are the points that are visible from our point of view, from the point of view from which we are sending the light to create the shadow? This paper gave us the inspiration because they created an algorithm to calculate what are the visible points, and therefore what are the points that I will help to create the shadow. And this algorithm is called the spherical flipping. What it does pretty much is that from the point of view, from the specified point of view, I want to understand what are the visible points of the object, in this case, the cat. And to do so, I flip the cat, and enlarge it exponentially from the points that are closest to the points that are farthest from the point of view. So that basically the cat, the visible part of the cat, the part that is visible of the cat from the point of view, is now on the surface of a sphere. So it's like a deformation similar to what you would do with a fisheye lens, or similar to when you reflect yourself in a spoon. Okay. When you obtained this deformed image, the visible points are the ones that are on the surface of this outer sphere. And you can use a very simple algorithm in 3D geometry, that is the convex hull, in order to retrieve what are the points of the mesh, in our case, that are on this line, on the sphere. Okay, so if we apply it to a human bone, here is a malleus bone inside our ear, we can see what happens. From the point of view, the malleus bone gets deformed. It adheres to this polygon that is the convex hull, and we can easily retrieve the points that are visible, the area that of the mesh that is visible from the point of view. Okay. Now, how can we use it to apply to bone and to be comprehensive of the whole morphology? That's very simple. We simply create, and there's all stuff that can be done automatically, we create a cage of point of view, so we can take a look at the object from multiple perspectives. And what happens when you do that, for example, here, if we try to understand the visible points from each point of view of this object, a skull, a cranium, what happens is that we see from each point of view something different of our object. Okay, here colored in different ways is basically each part of the object that is visible from one point of view or another. But in this case, it doesn't help us to reconstruct the internal part of the endocranium. Okay, so the brain endocast, because in this case we are pretty much simulating what a laser scanner does. Okay, because the point of views are outside of the specimens. So what we thought is, why don't we put the points of view inside the specimens, inside the brain case, so the only points that are visible will be the ones of the brain case. So we can collect this, the brain endocast that is usually takes a long time to do, we can collect it within minutes. And so we did, but we are even more smart lazy than you may realize, because we also find a way to recognize, to identify automatically the inside of the brain case the space, the area inside of the brain case, so that we can automatically subsample this space into a set of points that will be used as point of views. The whole algorithm, this part is particularly long to explain, but the whole algorithm has been published. It's available in R, in the package Arotron, and it's called Endomaker. Okay, so if you want to give it a try, you'll end up having beautiful results like this one. Okay, so you can see the quality is ensured by the fact that instead of any manual segmentation, we actually start from a mesh. So we use the quality is given by the interpolation that of the algorithm that creates the mesh from the CT scan. Okay, so that's why you can see so much detail. And it's a lot better. It's usually more detailed from what you can obtain by manual segmentation. And it also takes really just a few minutes, okay? And the endocast is not the only region that you can study through these methods that I just explained, but there is more. We published quite a few papers about these methods, so you will find different approaches by using the same algorithm, the spherical flipping. But as you can see, there is a lot of internal anatomy that we can access rather easily by using these methods. For example, you can isolate the complex vascular system of the very tiny malleus bone. Once, of course, you have the micro CT scan of the malleus bone, okay? And study this, it's possible using other things that I might explain in the second part of this slide in another example. And here is the other example. We have dealt with an example about a mesh application. Now we look at something that instead works directly on the CT scan, so on the volume, on the voxels, okay? And we deal with bone complexity. And when we talk about complex bones, of course, bone has itself a complex morphology, but nothing is more complex than what's inside the bone, okay? The cancellous part. As you know, there is a lattice of bone that helps in distributing the weight and the load, the biomechanical load, that is called cancellous bone. And it's hard to think that you can study something this complex using geometry, especially because the usual approach is to take a small region of interest, but this can be problematic because, like, for example, in the femur here shown in the image below, the cancellous bone is organized in bundles. So depending on where you put the region of interest, you will have one result that could be different from by putting it just a few millimeters on the right or on the left, okay? So an idea that I had in the past together with my colleagues was, why don't we just isolate the whole thing, okay? And try to study the whole thing together for, you know, a region that is larger than just a little cube or a little sphere. And so we started thinking about a way to isolate it directly on the volume, okay? Here, for example, I show you with a mandibular condyle, just because it's rather it's a rather simple morphology to follow with the protocol that I'm showing you in a moment. And what we do in this case is to use imaging operators, in particular what we call convolutional filters. Is basically the same stuff that you use when you want to blur or sharpen up an image, okay? And all comes up to this little matrix here in the middle that is called a structuring element. What a structuring element does, it's basically to apply to all the to every pixel an operation based on what happens around that pixel, okay? The structural element is always centered on each pixel, and this is what happens, and all the other cells around it is basically what happens, is the indication on what to do on the other pixels surrounding it. Pretty much how you see in this example here, the structuring element moves, and if it finds a cell that is full in connection with a cell that is empty, the cell that is empty in the following iteration will be full. And this is an operation that is basically called dilation, okay? And the opposite operation is the erosion. Why erosions and dilations using these 3D imaging filters are important? Because you basically can modify into a volume, you can modify the shape of an object by simply doing erosions and dilations, or dilations and erosions combined. What happens here, for example, in this example, you can see that the shapes here are connected to the smaller ones. Erosions allow you to lose the connections and lose small parts, but you can regain exactly the same shape, pretty much, depending on the structuring element, if you then let erosions be followed by other dilations, okay? So coupled together, erosions and dilations can help you remove connections or remove small parts, okay? And they are widely used in 2D imaging, but can be applied also in 3D imaging. And by using these imaging operators, we devised a protocol that pretty much works like this. We choose a region of interest that we, of course, want to study. We binarize it. This is all stuff that can be usually done pretty automatically with algorithms for thresholding, etc. When we have the binary of our 3D, I show you here an example in 2D, but it works in 3D. When we have the binary image, we use an imaging operator that is called fill holes, that actually it's based on erosions and dilations, in order to obtain our whole region of interest, the mask, okay? Our all objects, so basically filling the voids. And when we have the mask, we subtract the binary from the mask to obtain just the void part, which are then dilated and eroded in order to obtain what's inside, so basically a submask, including only the voids plus the trabeculae. We remove the inside from the mask, and so we obtain the compact bone isolated, and then we can remove the compact bone from the binary in order to obtain just the cancellous bone. And you can see the result that is pretty neat, and we tested in several other bones and it works pretty well. And actually here, I have an image to show you the different bones in which we tested and the results here in 3D on the right. And as you can see, this allows you rather quickly also to collect to separate the different parts of the bone, the cortical bone from the trabecular bone, from the cancellous bone, even in rather extended regions of interest, okay? So going beyond the classical approach of reducing the study of trabeculae to cubic or spherical samples. But this is not the end, because of course we can also study the extracted cancellous bone, that now it's isolated lattice of a very complex shape, by using skeletonization. There is another algorithm that basically converts a lattice shape into nodes and branches, and these nodes and branches can then be analyzed. All this I do into R, all this based on programming algorithm existing or that I develop. For example, to identify here in the head of the femur, we can identify the distribution of the trabecular elements in different species. So we can study, for example, how it changes based on locomotion, or also the resultant direction of the trabecular elements. Okay, this is as well an example that we use for locomotion, but of course it can be used for other reason as well. So this was my last slide. I hope you find this example enthusing as much as I find them. And I really thank you for having me here and for your attention. Okay, and I really, really suggest you to try this geometry coding couple. It's really something.
Awesome. Thank you so much for that great talk, Alessio. So with that, just a reminder that people can send their questions to the questions at PaleoPerks host, but we already have a couple questions. So yeah, I can just hop right into it if you're all good with that. I will post it in the chat here. 1 minute. Okay, so our first question, how easy is it to use methods on different groups of animals? For example, going from mammals to ammonites. Does it vary method to method? And I
Well,
guess just the various methods that you reported on here.
yeah, well, of course, you will use bespoke applications based on the specific stuff you're doing. But for example, since they deal with geometry, something like endomakers, something like the application for identifying skeletal cavities, that can ideally be applied to any cavity as long as you have it in your surface, as long as the CT scan that you did does recognize there's that empty part. Okay, so as long as you have a cavity, you can use the method in order to obtain the internal cavity in 3D, regardless of what species it is. Okay, it will work better in certain species other than others. For example, we find that on primates it works better, but we have seen that it works also in canids, in other mammals too. So, you know, the fact that they're based on geometry and on rather simple ideas, simple principle of geometry, it makes sure that they work on whatever looks like an empty chamber. Okay, so they can be applied with some caveats, but they can be applied to several species.
Interesting. Thank you. Okay, our next question from an anonymous person in the audience. Would the method used to characterize cancellous bone also work for identifying vascular canals in more dense cortical bone?
Yes, it would, especially the analysis that you that I quickly mentioned at the end. It's a type of analysis that can be also used for vascular systems. And if you do have and in order to the isolation part of the vascular system, yes, it would work as long as, again, with some caveats. It depends on how the vascular system looks in your binarized image. Okay, but if your binarized image does present the vascular system as a white pixel, and if that it's connected to other stuff that you want to remove, it could work. Okay, it's I present this kind of application for cancellous bone because it works very well with cancellous bone. it can work on other things, but sometimes, for example, I reuse the same method, I modified it a little in order to make it work on different structures. Okay, so the main idea, for example, um, this algorithm that I showed for cancellous bone is available in one of our packages, Indiana Bones, and that package clearly states that it has to be used for bone. Okay, because if I want to use a similar approach to another structure, I usually go look at the volume and maybe modify a little bit the the algorithm to make it work optimally on another structure. Okay, but the general idea behind it, the one of using erosions and dilations in order to separate parts of a volume and then recover the general morphology, that is universal. If you have anything that is reticular in nature, that is a sort of lattice, it's gonna work pretty much the same.
Great. Thank you so much for that response. It looks like Nicholas Schubert posted in the chat a question asking for tips for micro CT scans and primary bone specimens where there are a ton of very small structures in very close proximity.
You mean basically in this case, probably, well, you have to work on the segmentation. It strongly depends on how, what exactly are these structures. If you have a resolution that is high enough, for example, high enough, it's that if this like structures can be identified, like can be discriminated from one another by a couple of pixels, it could be enough to apply automatic methods to separate them. Okay, the point of the structuring element is also this: you can decide how many pixels you dilate and erode, and it depends on the size of the structuring element. Okay, if it's a matrix that is 3 by 3, you're just gonna erode and dilate by 1 pixel. So it gives you the chance to tune to the resolution of your scan. Okay, but in general, if you have low resolution, like if you have medical CTs, something like this approach doesn't necessarily work. Okay, for example, on the trabecular structures in medical CT, this tend not to work because the resolution it's not enough to have more than 1 or 2 pixels between like the cortical bone and the and structures of your interest. Okay, so instead, if you, and sometimes what happens is that if you erode, you can lose completely. So if you have a structure that is too little, you erode it, so that it's low resolution, you erode it, and what happens is that you're gonna lose the structure or features of the structure. So of course, you know, the classic adage, garbage in, garbage out. If your data is good, your result will be good. It's very difficult to make things work when the resolution is very low. So here we are talking about a rather precise method, but to have that precision, you need to use high resolution. Okay, but you could technically discriminate even smaller structures, and there are other methods to do that, other imaging filters. Actually, there's a playground of imaging filters that you can use to recognize different types of structures based on their shape. That's why it's so fun.
Okay, thank you. Okay, we have more questions coming in, so I'll keep them coming if you still have time, Alessio.
You have time, yes.
Um, so this question reads, thanks for the fascinating talk, Alessio. Can the EndoMaker package be used for reconstructing the interiors of invertebrate chambers or shells, such as crinoids or mollusks? And for starting off with the package, would an OBJ or PLY file be sufficient? Thanks, Neha.
Okay, thanks for the question. And the OBJ, PLY, or STL, they are all fine because the package itself doesn't read in the the meshes. You can read them through other packages like Morpho or RVCG in R, and those are able to handle STL, OBJ, PLY files. So that's not a problem, the one you're more comfortable with. It can technically be used on an internal chamber as long as you can as long as in your fossil, when you micro CT scan the fossil, you have um, enough contrast to separate within the fossil the chamber from what's filling the chamber. Okay, as long as it's a chamber, you'll be able to do that. Okay, uh, the 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 main use we have for it in anthropology is for the endocast, okay, because it's one of the major things that it's used in research. But for example, we in the skull as well, we have other um, hollow parts that we collect that are used less, but uh, our holes completely different from the brain endocast and still absolutely fine to use them. I've tested on other things as well. Sometimes even just for if I'm doing some CT scans for fun and doing some analysis for fun, I did test whether they work on other type of hollow chambers, and they do work. I never tested them on CT scan of ammonites or mollusks in general, but honestly, I would love to do that. It's just like I've never had myself any of these scans. Otherwise, I would have probably already tested it. But yes, it can be applied as long as it's a void chamber. It can be applied.
Okay, thank you. Okay, our next question comes from Nicola, and it reads, very cool tool. I spent months modeling endocasts of fossil internal ears. Could EndoMaker be used to model the ear labyrinth endocast, but also keep nerves and vascularizations as separate models?
Okay, with the internal here, yes, part of it certainly. I've never tried myself, but in theory, yes. If not EndoMaker itself, the algorithm on which it's based, I have been using it in instances in which the hollow chamber wasn't uh, like globular, like a brain. Okay, so for example, there are some brains where you have better results by applying directly the spherical flipping algorithm. And what you can do in that case is, instead of recognizing automatically the points inside the brain, the point of view inside the brain, you can define them yourself. So you can, for example, for the internal parts of the ear, you could put manually different points of view in the middle of the tube along all the area that you want to reconstruct in 3D. And if you apply the spherical flipping algorithm, you would end up most likely with a 3D rendering of the inner ear. Yes, it's something that I honestly have never tried, but since it's an empty chamber itself, but it's a more elongated one and more convoluted one, this is what I would do. I would do directly spherical flipping, and by using point of views manually collected along the in the center of all the structure that makes up the inner ear. But in theory, yes, I think it's feasible.
Okay, great. Thank you for that response. Yeah, hopefully it was helpful for the person who asked it. We do still have a couple more questions, so I will keep them coming for a few more minutes. So this question comes from Casey, and this question asks, for the endospace algorithm, is there a parameter or assumption that controls for bone thickness around the endospace? And how does the algorithm control for differences in bone thickness throughout the skull, if it can/needs to?
If you mean for the endomaker, no, it's not actually a problem. For the endomaker algorithm, there's no such problem as bone thickness because um, the geometry principle in which it's based makes sure that the deformation that occurs, it's not maintains the topology. Yes, this is the best way of saying it. Maintains the topology of the object. So whatever it's inside stays basically doesn't stay inside. So what happens is that when you deform it, what's inside goes outside, but everything that was outside goes inside. So what you see from the point of view, it's still only the stuff that you would physically see if you were the point of view. So it doesn't matter whether there is any anything related with more thickness of the bone or less thickness. It doesn't matter at all. The only two parameters are two parameters that are linked to the way in which the deformation takes place, but there's no concern in general about thickness. There is some concern about thickness in the second method I showed, that sometimes if you have very thin cortical bone, you can end up losing it. But the algorithm is conceived in a way that you always retrieve the information about compact and cancellous bone from the binary image. So that basically, even if you lost something, you go by subtraction from the binary image and the mask. So in that case, in the other method, bone thickness is much more a problem, but it's solved this way.
Okay, thank you so much. We have one final question here, and I think this is kind of a fun one to wrap us up. This person asks, some of these meshes look a lot like game polygons. Is there any use of game engine software in your work?
I don't know. I think you mean probably, I don't know, this one are the ones that look more I don't know, colorful game style. I have no idea. Technically uh this one itself, the spherical flipping, it's something that has been patented because I believe this might have been used in software engineering or for game design. It may have been to reproduce this thing about the shadows. But I wouldn't know exactly the follow-up of this research besides the one, our own application. But ideally, yes. Probably not using R's, probably not with the implementation that we did in R, but if you re-implement it in C++ or in Java, you could definitely have the speed of computation that is needed for game design, yes. So technically, you could be able to use them for any idea about game design if implemented somewhere else than R.
Okay, super interesting. Well, thank you so much again for all of the super thorough responses to these questions, and for of course, for the presentation.
Thank
Uh,
you.
I will just kind of wrap us up here. So thank you everyone for joining us today. Thank you for all the great questions. Um, I think it seems like a lot of people learned quite a lot and from the talk, and hopefully we'll be able to apply some of this to their own work. So thank you, Alessio, and thank you to those of us or to those in the audience. Just a reminder to please fill out the weekly feedback form, which will be shared in the chat again, so that we can learn a bit more about who attended today's seminar. You can join us next week on May 13th to see Elizabeth Seibert talk about paleo fishes and other things in that direction. So we look forward to seeing everyone then, and have a great rest of your day, or a great rest of your morning, or a great rest of your night, depending on where you are. And we look forward to seeing you soon. All right. Thanks, everyone.